Welcome back, guys. We are going to study now application of gas power cycles. The general analysis that we described in the past video, we're going to apply it to two well-known cycles, and those cycles are the Otto and the diesel cycle. So let's start with the Otto. Otto cycle is the ideal gas for spark ignition engines. We will try to do it for with a Carnot cycle, but in a TSI, you remember that it was square, and we have something that is not close to that. This will be an actual PV cycle for an actual internal combustion engine, a spark ignition engine. You can see that this engine has a compression ratio of 8.4, 3500 revolutions per minute, and initial temperature of 0.4 atmospheres, and mean effective pressure of 2.9 atmospheres. Okay, so this, which is the actual cycle, we will try to mimic with this cycle. You can see that we have an exhaust to intake, then we have a compression, we have the end of combustion, the expansion and exhaust. This is a close representation of this actual cycle. Now we're gonna do a further simplification. We can see that this line here we can neglect it, since we have inlet, intake and exhaust. But we are going to consider our system a closed system with a fixed mass, so we don't have inlet or outlet of gas, so we get rid of this part. Then this compression, we're gonna model it as an isentropic compression. The expansion, we can also model it as an isentropic expansion. Now, you can see that in the combustion process, we have a very little change of volume. The combustion is so fast that we don't have practically no change of volume. So we can model this combustion as an constant volume heat addition. Here is a little bit more of while, because we don't have exactly constant volume, but we can approximate it that way in looking for simplifications. As we described in past videos, this cycle will occur between the bottom dead center and the top dead center. So here we have the cycle that we're going to analyze. We have an isentropic compression. We compress air. Then when we get to the top dead center, we add heat, keeping the volume constant. Because of that heat in the air, we increase its pressure, and we are going to expand the piston. This first piston moving up, we call it the compression stroke. Each stroke is the movement between the top dead center and the bottom dead center, and vice versa. So in this expansion stroke is where we move the piston down, or is also known as the power stroke, because this is the stroke in which we are going to get power. And then we are going to reject heat as a constant volume. So this is the Otto cycle, and this animation you can see that we have the piston moving up and down, and if we count it, let me just fix it a little bit. Inject here, and we need two strokes. That means 2 complete revolutions. Let's count it. 1, 2. We need 2 complete revolutions in order to complete 1 cycle. And this, so that's why we call it 4-stroke cycle. Let me take it a little bit back, and we are gonna describe each process. Okay, so we have intake, fuel, then we compress it, we spark here. That spark will create a combustion that will expand this piston, and then we're gonna move our cylinder upwards so we can move all of this combustion residual to the outside. And then we start again by admitting new fuel. Okay, so we can summarize. We said that the first stroke, 1 cycle have 4 strokes. We said 1 cycle have 4 strokes, so we need 2 revolutions in order to complete it. We have a variation of this, which is the 2-stroke cycle. In that cycle, you can see in this diagram that the intake port and the exhaust port are connected. So we need just 1 revolution to complete the 2 strokes, and that 2 strokes will complete one cycle. These are used for very simple machines like motorcycles, little machines. So to summarize, we are gonna have an isentropic compression, constant volume heat addition, isentropic expansion, constant volume heat rejection. So what will be our analysis for this cycle? So we're going to start with our first law for closed systems. We're going to start by we're going to do it on a specific quantities. We're going to have work in minus work out plus Q in minus Q out equal change energy that we know is U2 minus U1 plus kinetic energy 2 minus kinetic energy 1 plus potential energy 2 minus 2 potential energy 1. We know that we can disregard this since we are not going to move the whole system or going to change altitude. So this will be our basic equation, both for for both the whole cycle. So let's start with, for instance, with the compression. In the compression, we're going to move from the bottom dead center to the top dead center. So analyzing, we know that we have work in. We're not going to have work out. Since it's adiabatic, we have Q in and Q out neglected. So we're going to have work in equal U2 minus U1. And remember, we can analyze this two ways: constant specific heats, in which case will be Cv T2 minus T1, or variable specific heats, in which case U2 and U1 from table A17. Okay, if we do the same analysis, and we're going to repeat it once, and then the other two will be left to you as an exercise, we can compute the heat addition process. In this process, we have we don't have any work in, any work out, because it's a constant volume. So we're gonna constant volume. We have Q in. Obviously, we don't have any Q out. And then we have the final state is U3 minus U1. Same consideration as here. If we repeat the analysis, we can get these expressions. Q out will be difference of U4 minus U1. If we want to compute work out, will be U3 minus U4. Now, if we analyze with constant specific heats, we'll recall these expressions, and if we apply them to find out every single temperature, we're going to arrive with this equation. We should recognize that there's a parameter that we already described when we describe the internal combustion engines. That is the compression ratio. This compression ratio is the maximum volume divided by the minimum volume. The volume that we have at the bottom dead center divided by the volume that we have at the top dead center. In this volume, please notice that we have the dead space included. Now, this is true, and let me just put and I will do that in red. Oh, sorry. This is true only for constant. This is true only for constant This is true only for constant specific heats. For variable specific heats, you need to compute the traditional way. Two things that we can learn from this expression is that our efficiency will increase with the compression ratio. This compression ratio cannot go infinitely high we have a short range, and this range is limited. Above the certain number, we're gonna have what we call knocking, because the fuel mixture will auto-ignite before going to the top. As we discussed in class, this is actually the limit for a very efficient and very complex cars like a Porsche. Second thing that we can learn is as we move from different K values will change our efficiency. The lower the efficiency will decrease in the direction of decreasing K. This will be more close to what a polytropic process, a real process will be. So our assumption of an isentropic at ambient will always at atmosphere cold conditions, which will lead to 1.4, will always give us a higher efficiency than what we really will have. In the next video we're gonna solve problem. We'll have on the next video we're gonna solve a problem that will help you to remember what we discussed in class. Thank you guys.